This afternoon we've got two talks before the poster session. So we're going to start off with a stats one now, and I'd like to welcome Paul Gosling from the University of Leeds.
Thank you, Lindsay. Thanks for inviting me to talk. I should say it is kind of stats, but I like to think there's a lot of pure maths in here as well. Some real hard geometry. So this is work with Chris Pope, who is here, my PhD student, Joel Johnson, who provided the application that we'll talk about a bit later, Stuart Barber at Leeds and Paul Blackwell at Sheffield. So this is work talking very much about surrogate models and how to build a surrogate model where we've got particular features in the thing that we're trying to model. So in particular, we're looking at discontinuities in some kind of spatial field or over some kind of input space, and we're going to try and model these using Voronoi tessellations. So we're going to go on and start with why do we bother with discontinuities? If there are discontinuities there, how do we build a surrogate model over it? How can we split up space? So there's very many different ways of doing this, and I'm going to talk about ways where we actually split up space and try to fit individual surrogate models to different parts of space, although there are other ways of thinking about it. I'm going to say, well, okay, so we've got this problem where there's discontinuities. How do I go about sampling from my input space, for my computer model, say, to find discontinuities? So it's a little bit different from trying to find a good surrogate model where there's no splits, where you're trying to get an appreciation of the correlation structure. Here we're trying to not only get an appreciation of the correlation structure, but also where these splits are in the process. And I'll finish off with application in climate science. So a bit of motivation to start with. Of course, heterogeneity occurs often in spatial processes. Here we've got the rainfall map for Great Britain between 1981 and 2010. You can see it's very wet up here in the north of the country and very wet in Wales, but there's real breaks here in the behaviour. So if we're trying to fit a process to this kind of data, then we struggle to capture these features which are close to the boundaries. So in particular, if we try to fit a Gaussian process model to this, we'll smooth over those boundaries often, and we won't capture the differences correctly, perhaps. Another one that I'm going to talk about is the ammonia concentration. Again, not a computer model problem, but it's just showing something where we've got heterogeneity over a field. What's quite interesting about this particular map, you won't be able to see these numbers, but these are the recordings of the ammonia ion concentrations at these particular places, and where it's more red is where there's a higher concentration, and this is where they do a lot of some of the farming, and there's a real difference in the way that the land is set up there. One of the interesting things about this particular graph is that this is actually a Krieg estimate. So you can see how nice and smooth this evolves over the United States. But in reality, it's far more jagged, and we're going to show how we can use, we can look at this data and try to capture the discontinuities in this process. The real example we're going to use the climate model, which is a bit bigger, where we've got an expensive computer simulator, where we're trying to capture the behaviour of this simulator. In particular, we're looking at modelling clouds. So here we've got some model output, cloud fraction, and we're looking at two inputs of the model, aerosol concentration and some mysterious theta. I don't know where it is. I can't even pretend that I know where it is. But what we've got is a region here where the model is well behaved. So for this particular setup of the model, we expect to have a really high cloud fraction. So the scientists say, yes, this is what should be happening, but then we've got a ridge where it falls off to poor behaviour. So the scientists want to know, well, why is that happening? Is it a problem with the model? Is there something physical about that particular area? So it's trying to find where this ridge is. And of course, if I try to fit a Gaussian process or some other regression model to this here, it would very much struggle to capture this edge for us. So, in the competition, who's got the fewest equations? Today I'm going to win because there's only really two, I think. And of course, this morning we've already heard about emulation and Gaussian processes, so I don't need to dwell on this too much. So, but what you can know for the more technical-minded, I suppose, we've got a Gaussian process which is a prior over our functions. We've got some mean M, and we've got some correlation functions C, and some sigma squared. And essentially what's going to happen is we're going to observe our function, our expensive function, or spatial process at a limited number of points. We're going to use these data to update our prior. And in what we've done, we've used both Gaussian and Matern correlation functions. Now, just to show you why we can't use standard Gaussian process models, I'm going to start with a nice 1D example. So we've got some model, f of x, and it just happens to be a straight line. And we've got x here on this axis, so we vary it between 1 and 10. And I've managed to evaluate this very, very expensive straight line function at 6 or 7 points. You can see here, well, you can't see, there's a red line and a black line. So the black line is a true function, this straight line. And the red line is my Gaussian process mean. So you can see it's just lines throughout top. So yes, the Gaussian process, it can capture a linear function. Brilliant. And it can do it very, very well. Of course, what I'm not showing here is actually the still uncertainty away from those points. But I'm just going to concentrate on the mean of this particular process at the moment. So as I start to introduce a discontinuity, you'll see it doesn't perform so well. So in between these two training points that I've got here, I've introduced a discontinuity. So the true process now is this black line, that it jumps, and it's this, so it's a piecewise linear function with a true discontinuity here. And you'll see that the Gaussian process obviously doesn't know that there's this jagged part here, and it's just trying to fit as smoothly as it can, trying to adhere to the smoothness properties of whatever correlation function we've put in, and it's compensating. So as we make this worse, obviously it gets a little bit worse. So you can see here what's happening is we need, because of the choices that we made in the correlation function, we need it to be differentiable so many times. So for this underlying function, for the Gaussian process to be differentiable, we need to compensate here. So it instead of going straight and then down and then straight, it's got no idea there's this break here. To be differentiable around these points, it needs to actually go up here, because there's no way it could just go flat, 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 and then drop and still be differentiable. So it's just really not coping with this, and of course, to make this bigger, that goes in. But of course, what also I could have done here is I could have changed where my data points are. So as I get closer and closer to where the discontinuity is, I've got 2 points here which are closest to discontinuity, and it's this gap which is driving a lot of this curvature further away. As I bring these 2 points where I've actually observed the process closer together, you see again it's having to do a lot more work to try and keep things nice and smooth. So you'd think, if in one dimension, in this kind of problem, you'd be absolutely crazy to actually do anything like this. You just look at the data and you know that there's something strange going on, right? But when we're looking at these expensive computer models, we're often faced with problems in very high dimensions. We might not be able to see these things so clearly. So we might miss this type of behavior. So we could fit a Gaussian process which looks nice and smooth, it might have some good properties, but we might have just kind of smoothed over any discontinuities like this. So just to go on from here, ways in which we can actually break this down and split up the space. One way that people...
I don't know.
Sorry, Christoph.
Questions, or we can...
No, come on, please.
Okay, because this example here, this can you... Yes, this. So this is, of course, reminiscent to the Gibbs phenomenon in spectral methods. So you are collocating and you have a discontinuity, but you pretend you don't know that there is one.
That's exactly the same, if you ignored it.
And then you would... What you say is then the approximation is bad, which is doesn't need to be said. But the question is somehow in this red approximation, is the information that there is a discontinuity and where it is located, is it somehow still hidden, even though the graph looks bad? And in spectral methods, there is a theory which the answer is yes. And you can extract it, even though the plot of the fitted object is extremely bad. The information about the discontinuity, the height, and the location is exponentially accurately encoded in the data you have for the red. And you can extract it by some filtering. There is a specific post-processing So this is a work which was done in the 90s by David Gottlieb and people not in statistics, in numerical analysis, that do have a systematic, mathematically solid methodology to extract out of such overshooting fits the location and height of the discontinuity at high accuracy, post-processing the fitted object.
I think in a way that we've actually decided out what correlation function we're using, probably we can't recapture that information here. But there are other decompositions that we could do where we would, even though our approximation would be pretty poor, and it show up as being pretty poor in the kind of predictive sense, but there would be ways that we could actually get back to that if we were a bit clever with what kind of covariance function we've got. But here we've assumed in our underlying approximation that everything's really, really smooth. So the information in a way is lost, I think, then.
Maybe we talk later about it, but I wouldn't say that right away.
Probably because, yeah, I see what you mean. So because there's this really strange behaviour, maybe we can try and see what's underpinning that, and then whether that falls out, it's kind of spectral analysis.
Yeah, it's one has to do it, but anyway, we maybe talk later.
Yeah, sure. So, assuming that we want to use something like a Gaussian process to fit this, and we want to try and break it up into different regions, there's very many ways that we could do this. And one that became quite popular around 10 years ago is using essentially classification trees. So here we've got an example, a very simple example of a classification tree, deciding on whether or not somebody would buy a house. And they were split up by different incomes, and then the number of family members, and then the number of years of education. So this really is splitting one variable at a time. So if their income is above 75,000, then they go into this node, and so on and so forth. The way that it applies to these kind of computer models is that we're going to look at each one of the input variables and start to split that up and say, well, we're going to, if it's above a certain value, we're going to fit one Gaussian process. If it's below, we're going to fit another. We're going to keep dividing up space in that kind of way. And this gives rise to treed Gaussian processes, which again were developed probably over 10 years ago now. I'm going to show you a quick example of treed Gaussian processes in action for an example that they gave in their paper, where we've got some model of lift for an aircraft, and you've got two different inputs into this model. So you've got speed and you've got an angle of attack. You can see that for the vast majority of space, lift is behaved really quite well. It's quite a smooth behaviour. Then you get into this kind of corner here, and it's really quite nasty behaviour. So it's quite a difference. So again, if we're trying to fit a single Gaussian process with the same correlation structure across, we're going to struggle to model this. So in particular, I'm not sure how well these are coming up on the screen, but these are the divisions suggested by the treed Gaussian process. So you can see every division is orthogonal, so it's always perpendicular splits. So the first split here is decided to split it at 5 for this alpha parameter, and said, well, there's something different going on at this bottom end than there is to this top end. And then it's gone on from there and said, well, we can keep on dividing this up and trying to make it into smaller chunks where we can actually try to capture the different features. So in this particular area here, where there's highly nonlinear things going on, it seems, we've got quite a few different splits, and actually quite a small slice there has been taken to try and capture that different type of behaviour. So the point would be is once we know these kind of splits at the same time, we're trying to fit Gaussian processes to each one of these, and we've got a model where each one of these different rectangles has got its own Gaussian process. So we can measure. Sorry, go on.
What's the criteria for splitting the domain, and then is it done one parameter at a time? I think I heard you say that. So is this done in the speed direction and then in the other direction, or is it done simultaneously?
It's so the one that's best is chosen. So it's the one. So you're trying to do. You're exploring your likelihood. So you're trying to see what division of space, in terms of these cuts, are going to best explain your data.
What does that mean by best? What's the criteria is what I'm saying.
So you're trying to max. So you come up with a posterior distribution, so you've got some prior over the various treed representations that you can get. And you're trying to find the minimum number, I suppose, of Gaussian processes which will fit the data well. So it's a likelihood based. So obviously these are all orthogonal, but we could have much more complicated pictures. So to extend this, around the same time, people were using Voronoi tilings to define different parts of the space. So for those of you who don't know what a Voronoi tiling is, essentially it's a set of tiles which are absolutely defined by the center. So if here you see these black dots which are the centers for the Voronoi tessellation. If I want to know if you're on a tile in a Voronoi tessellation, I take a point, like that one there, and I say, well, which center am I closest to, and that's the tile that I'm going to be on. So mathematically very simple. In 2 dimensions, very easy for us to draw it. In multiple dimensions, it's very easy to calculate it as well. So here we've got a situation, we've got a tiling which can break up a space, but all we need to do is to define where the centers are located down these centers that we've got. So in a similar way that we would try to find in the tree situation, we try to find those cuts which are best to try and split the space up so we've got individual independent Gaussian processes working on them. We'll do the exact same thing here for the Voronoi tessellations. Of course, you'll notice that all the tiles are convex, which is no surprise, seeing as we're working in a Euclidean distance here. So what we will do is not only will we, so this is a simple Voronoi tessellation, not only do we allow the tiling to define where the breaks are, we will also have Gaussian processes defined over multiple tiles. So it's a little bit different from what they did originally in the tree Gaussian process. So what do I mean by this? Here we've got a tiling on a 2D space where we've got 5 centers, and these are the 5 tiles. What we can do in our method is we can say, well, this tile and this tile, the function seems to behave very similar over these 2 tiles, so why not build a Gaussian process over both of these, and then we've got another 2. And of course, these regions, which are made up of multiple tiles, don't need to be made up of neighbouring tiles. So that gives it a lot of flexibility, and of course now we don't need our regions to be convex. Because once we start adding these tiles together, we can get much more complicated shapes, if you like. So this is the basis of the entire model. So the input space is going to be divided into these disjoint regions, and on each of these regions we fit its own Gaussian process. So essentially we're just going to get, because we're assuming independence across these Gaussian processes, we're going to multiply together the likelihood functions, and because we're doing this in a Bayesian way, we have to put a prior across all these things. So this here is just a multivariate normal. So at the index xi, where we actually look at the function, we've got different yi's, which are the outputs, and this is distributed as a normal distribution which depends on its whatever roughness or smoothness parameters we've got for our correlation function, whatever kind of variance we've got for each one of the Z Gaussian processes. We might have regression functions as well on each individual thing. So typically we will stick to just having linear functions as our global part, is what Michael was saying yesterday, for our Gaussian process, and that's where these betas come from. And then we've got another vector here, t, which is essentially our tessellation. So our tessellation is going to tell us where each one of these points that I've observed sits. So which Gaussian process does it belong to? So of course I need to come up with a prior over all these different parameters. So just a little bit on the prior. For the prior for the roughness parameters, for sigma squared, and for the regression part, for the global regression part of the Gaussian process, we use just standard Gaussian process things in that, so inverse gamma type priors and normals. For the tessellation, it's much more complicated. So you have to break that down into several parts. So we've got this prior distribution over a tessellation space, which essentially is a number of centres, which we call n, and then we've got another vector here which is a centre, so that's the centre locations. So we have a joint prior over that, and just to start off we've used a Poisson point process for that, and with some sensible intensity, I say. Of course this is prone to clustering, which may have issues. So when we have points with centres which are very close together, very small changes in the centres can really change the tessellation very, very strongly, whereas if we've got points that are far apart, very small changes in these centres are not going to change the tessellation a lot. And this can affect how we do our MCMC when we're actually trying to estimate these models. So we might actually put in a point process there with some kind of repulsion term. So we try to extend this. So this first bit is a prior for the tile centres and their location. Of course, once we know how many tile centres we've got to think about how many regions we're going to form over those tile centres. So Z is a number of regions, and a kind of vanilla thing we would do is put a discrete uniform over those. And Q is going to be an index set telling me which centres belong to which region. So once I know the number of regions and I know the number of tiles that I've got to think about how many different ways there is of partitioning these tiles into those particular regions. So this is to do with the Bell numbers. So this is quite a vanilla prior, really, because we're using discrete uniforms over everything, and a Poisson process is that with that intensity that we've used is not really telling us too much. If we truly knew that there was two regions, two areas of behaviour in this function, then we could actually put this in and put in much stronger prior information if we desired. Although this is what we've used going forward in the examples I'm going to show you. Implementation is rather tricky, and we use reversible jump MCMC. Essentially what we've got going on is standard Gaussian process fitting in a Bayesian sense within a birth, death, move and relationship change metropolis Hastings algorithm. So birth, death, move, what am I talking about? Well, you've got these Voronoi tile centres, and a new tile centre might be born, and that will change the tessellation. We might take a centre out, so that would be death, and that will change tessellation. We might move any of these centres around, and again that changes tessellation. The relationship change is actually changing from having a tile in one region to another region. So again, it's trying to form these more complicated shapes within the Voronoi setting. So this, our kind of very naive way of doing the MCMC shows the kind of difficulties that we're having. So in particular, we're running 100 MCMC chains from random points, and we're running each chain for 10,000 iterations. We're checking for convergence as best that we can, and then we hope that we've got something that's converged. This is tremendously difficult to do. And one of the reasons, although we're Bayesians, identifiability, if we've done the priors right, maybe shouldn't be too much of an issue. We've got big issues here in the MCMC and in the tiling because, as I was saying, very small changes in the positions of the things won't make a difference to the likelihood calculations. Also, you can imagine there's very many different tessellations which would do the same job as a couple different tiles together. So we've got these local maxima and identifiability issues. Of course, whenever we do any of this type of expensive MCMC, we should really try and check robustness of what we're doing. And we're starting to develop methods for checking robustness for each one of these different choices that we're doing. But that's again proving to be very expensive, but something that we're working on. So I'm going to show you an example now of this actually in action. It's going to be a two-dimensional example, so a bit more complicated than the 1D example that I had, but not too much more. So I've got one input dimension here and another one there, and it's another step function, so we've got something that's really low, 0-ish, and another one that's quite higher, so this is about 12. So there's a true discontinuity here, so this is basically a flat surface here with a step up in the middle. And I just happen to choose it to be a square which has been a little bit rotated. And I'm going to compare this with the tree Gaussian process, right? So they all depend on it all being nice and square, so I'm kind of cheating already. Of course, if you knew this kind of thing was there, you'd just rotate the space and the tree Gaussian process will work very, very nicely. So I fit the model. You see here these little dots, so this is where I've actually evaluated the function, and we've got these crossed squares there, so there again where we've evaluated the function, but they just happen to be inside the discontinuity. So you see that the standard GP model, which is plotted here on the right, is not coping so well. As a matter of fact, we had real issues just fitting a standard GP to this, so we needed to give it quite a nugget to actually get it to be conditioned well. But you can see the same kind of behavior that you got in the 1D, where you've got these kind of periodic features coming out, where it's trying to compensate for the shift, for missing the discontinuity. You see here for the Voronoi, again, this is just a predictive mean, so there's actually, it captures this middle section really well, but near the borders there's quite a bit more uncertainty, right? Which is where it should be. If I compare this with the tree Gaussian process, well, it does all right. I mean, what can we expect? I've kind of made it as bad as it can be for it. But it does catch that middle point. You can see how it's cut off, and it's isolated the other areas here relatively well, given that the data that they've got. And it's doing a very good job of prediction away from the corners of this strange discontinuity that I've set in. If we look at the map division, the maximum a posteriori division, which comes from the tree Gaussian process, that's the kind of picture that we've got. So they've got a one Gaussian process fit there, and then 4 others. But of course, when we come up with this predictive mean, we're averaging over all possible divisions and the kind of uncertainty that we're going to get in the function fits on each one. Well, that's really difficult to see. So these are 4 tessellations taken from our method. So these are 4 possible tessellations coming from the MCMC chain. And again, I've marked out the black part there, which is the true discontinuity position. And for most of them, they're doing pretty good. There's some kind of tile in the middle that's capturing most of this behavior. But you'll see in some of them, they're actually splitting out. So these 2 at the bottom, we've got maybe 2 tiles that are covering this space, and perhaps 2 tiles here. And what's happening is that you're getting one tile which is saying, well, things are pretty much flat there. Then you're getting another tile which is saying, well, we can actually do a good job just putting a nice linear function here as well. So a Gaussian process is fairly flexible, so it's able to fit this okay. If we look at the predictive mean alongside the standard deviation, so you can see that these kind of white patches is where there's going to be a bit of uncertainty, because that's where the tessellations are being changing from one step in the MCMC to another. But you can see this is the area here where we've got most predictive uncertainty. So up there, we're not sure if these points here are forming their own little process with these extra points, and a nice straight line linear fit is actually doing very well here or not. We can also, like we did for the treed Gaussian process, we could think about the map tessellation, and this is our best tessellation in some sense. So again, we've got one tile here which is capturing all the points, and that point there is actually in this tile rather than that tile. So that one, it's got the process. It's not absolutely sure where the boundary is. Of course, it's quite far away here. But there's no data points there to constrain it, so that's probably understandable. And also, if you look at the number of regions, what's going on is that we're fitting one Gaussian process to this middle tile, and typically we're fitting a Gaussian process to all these points on the outside simultaneously. Now, if we look at we can look at the number of regions that come through our MCMC chain, so our posterior for the number of regions. Although the best estimate has only got 2 regions, actually a lot of times we do get free regions. So there's a lot of the features that are happening where it's actually capturing a kind of linear function on the edge of this. Again, with more points closer together, I think we'll start to eliminate this. So just to be fair to the treed Gaussian process, we will do another example, but I'm going to rotate that square. And again, if we fit a standard GP, we have issues. You get a nice picture that looks fairly symmetric, but it's trying to compromise really what's going on at the edges. So you get this kind of smoothing over where the discontinuity is, exactly like what we did in the 1D example. The tree Gaussian process does really well at capturing these boundaries as it should, seeing as it's set up in that kind of orthogonal manner. And the Voronoi one does reasonably well. Not quite as good as the tree Gaussian process, because the tree Gaussian process has got that prior constraint that those are where the directions of any discontinuity is going to be like that, right? I've said there could be any angle. So you can see there's actually a fair bit of uncertainty around what's going on in this edge, where we've got very, very few points. For the treed Gaussian process, because all the cuts are going like this, it's borrowing strength from having information down here and here to actually get out that corner a bit better. But here, I don't really know what's going on to train the Voronoi tiling. Although if you look at the uncertainty, like I said, there's a great deal of uncertainty around these points. Now, strangely enough, these are the map estimates, the map tessellations from each one of the methods. So the tree Gaussian process gets it always bang on there. Ours has got a very strange spike coming out, but again, we don't really know. But one interesting thing is the mean squared error prediction at some validation points. So we basically put a grid over this space and calculate the mean squared error. And as a matter of fact, our method is doing better. The reason our method is doing better is because we used an off-the-shelf version of the treed Gaussian process where we fit individual Gaussian processes to each one of these tiles. So you lose a little bit of strength. Whereas with our method, we share information across all these because they're all in the same region. So the prediction is just slightly better. But of course, if I allowed a Gaussian process to be shared across these tiles, this would outperform this, I think. So just going on to an example in spatial stats, the one that I mentioned earlier, where we've got the ammonia concentration at ground level for 250 US sites. So we've got the US states there and a couple of US overseas territories down there. And you can see, maybe, the colours maybe not so great, but we've got this eye area in the middle there, and we've got more of a smudge going over this side, so you think a Gaussian process might be able to fit this rather well, because it's not a great one, but there's a bit of a jump off here, and actually some really quite low values in the middle of these, and some eye values popping out on their own there. So a Gaussian process might do very well here to get this, but when it starts moving on to the eye areas at this end and dropping back down, there's a lot of changes, very fast changes, so the length scales are probably different at different parts of the map. And I'm going to show you now the tessellation. This is a map tessellation that we've got. And you can see the boundaries of the tiles and the centres are coded. So if they've got the same symbol and colour, that means that they're on the same region. So over here where I said it looked rather smooth and we might be able to fit something, you've got the same Gaussian process fitted to this entire region. Interestingly, it's the same Gaussian process which surfaces over here and here and here and here. So we're sharing information across this entire space. When we get to the middle where with the eye things, they've got their own Gaussian process because they've got different behaviour. And then again, we've got some that are going off here, which strangely, these are very low areas and these are very similar to the kind of things we expect near the coast. So you can see how I can share information across different locations, even if they're not neighbouring tiles. But we can split this up and keep the discontinuities going. So in particular, that's the mean surface from our tiling. So it's not as smooth as a Creed surface that I showed you right at the start, with that picture that they produced to put on their website. And it captures the kind of features that we're getting down here, where we've got you've got a very well, relatively high one there. You're very close to some very, very low values all around this area. And actually, the uncertainty in here is very, very great about what's going on. And over here, it's much more well behaved. If you compare that with what you would get if you did a standard Gaussian process, you get something more like that. So just blindly fitting a Gaussian process to this, what it's done is it actually does a reasonable job over on this side, but then when it gets here, it's not doing so well. And the reason that's doing a reasonable job over this side is because it's pretty flat. So it's got some kind of constant mean here, but then there's got to be departures here. And you can see that it's going to have very short length scales. So it's trying to capture these features. So not so good, perhaps. So going back to one of the reasons that we're doing this, it's not just so we can build predictive models and improve that and get discontinuities into these models. It's actually trying to find where these discontinuities are and to tell scientists where there might be issues in the models as well. So when we think about maybe improving estimation based on these types of models, you might think, well, we might just target areas with high uncertainty, which is a reasonable strategy. You might just think, well, I need to continue with the space-filling theme, so I need to try and get every part where I've not already sampled and see what's going on with a function there. Or we might be much more direct, and we might try to target those region boundaries. As I say, we're interested in telling the scientists where these boundaries are, so if I can try and pin those down a little bit better. Now it turns out actually that the points where we're really uncertain about where the boundaries are coincide with the areas of high uncertainty as well. So these things are not mutually exclusive, if you like. So finding points that lie on a boundary in 2 dimensions is relatively simple. The geometry is very simple. I know it is because I can do it. The difficulties come as we start moving up the dimensions. So 3 dimensions, it's very difficult to characterize these boundaries. I think once you get above 3 dimensions, it's pretty much impossible. So you can characterize them in the sense that I can tell you about whether or not a point is at one side of it or the other, but I can't give you the mathematics of it. That's the point. Which is a bit odd for something that's so simple, perhaps. So the way that I do it, I'm going to demonstrate obviously in 2D so I can actually visualize what I'm doing, but I'm doing this in high number of dimensions, is I think, well, this is one of my tiles and I want to find the boundary on this tile. So what I do is I look at the center and I center a multivariate normal distribution on that. I give it a multivariate normal with center, with the mean the same as the center, and with covariance matrix, the identity matrix. So I've got these independent Gaussians really. And what I do is I draw at random from this Gaussian, and that turns out, because our Gaussian density is symmetric, that when you do this and I just draw a sample from it at random, I actually get a uniform direction. So it's equivalent to uniformly getting a direction between 0 and 2 pi. So here I've found a point, that's my random draw from my multivariate normal. That gives me a direction to look in. Then what I do is I just project along that line and it becomes then a one-dimensional search. I just see when I skip from one tile to the next, and that tells you where the boundary point is. The 1D search is much simpler than trying to do something in multiple dimensions, although there are issues with this. So here's a problem where I've got 5 centers, and I'm trying to find the boundary for this middle tile. So I've got the 5 centers here, and what I've done is I've sampled from the multivariate normal around here, and I've gone off and projected and found where these boundary points are. So you may see what kind of issue I'm going to have to start using this sampling technique. It's not going to be the best sampling technique in the world, that's for sure. And of course, as I move these centers, so I'll move 2 centers a little bit closer here, so that one's moved a bit closer to that one, you see the kind of issue that I'm going to have. And as I get very close, we find that we're kind of missing areas, because there's very, very little chance of finding the angle, right, to hit those points. but I'm sampling lots and lots of points here. Now it turns out this is very, very computationally achieved, even in high dimensions, so I reckon we can just throw a computer at it, although I'm not so convinced about its performance in very high dimensions, but up to 6 dimensions it seems to be doing rather well. So if I just do this millions and millions of times, I can find very many points that fit. So there might, relatively speaking, there's only a few points down in these corners, but at least I've got some good candidate points here. So the algorithm that we use is we're going to randomly choose a centre within the region of interest. So the idea is I want to find the boundary of this region of interest. I randomly choose a centre within that region of interest. I randomly choose a point on the boundary using that procedure that I've just done with all its deficiencies. We check if that point's on the edge of a region, because of course when I'm looking at these tilings I could have 2 tiles which are close together, and a region might actually include a tile boundary. So I check if that point's on the edge of a region. If it is, I'm going to keep it. I'm going to keep on going and doing this, and this is going to be a candidate set of points on my tile. Sorry, on the region boundary of interest. Once I've done this and I've got a massive candidate set, I then think about that space filling property, because I know these are going to be the areas where I'm potentially most uncertain about. So I find points in the candidate set which are furthest away from the points that I've already sampled the function at. And I keep on doing this until I've got enough points in my training set. So I add one at a time and keep finding the next one that's furthest away, but I know is on my boundary that I've estimated so far. So back to that example where we've got this rotated square. We decide that we need 5 extra points. So this is our original, and this is one of our map estimates based on this particular data. This is our map estimate based on this data. So we pick 5 additional points. So what I would have done is we choose one of these tiles at random, and we start to look for points on the boundary. If it's on the outer bit of this region, we'll keep it in our candidate set. If it's not, we'll keep it out. And then once I've done that, I look at all the points that I've picked along this boundary edge and say, well, which ones are furthest away from the points that I've already got. So it's kind of maintaining a space filling idea. And in particular, the 5 red ones are the ones that we found for this particular problem. So with the first data set, we get something like this. We add points to it, and we can start to get, as a matter of fact, we added the point here, so we're doing a little bit better down in this corner here. We're still missing information about what's going on here. But you see that if we showed you the uncertainty there, we're actually getting much more certain. So we're getting much more certain about what's happening with the boundary and trying to find where that discontinuity is. Now there are arguments about whether or not just doing one point in that direction is a good idea, or whether you want to do multiple points in one direction near the boundary to see if you can capture both sides of it, something close. But then there might be a lot of redundancy because you're not sure whether you've actually sent multiple points over the edge of the boundary or whatnot. So there's many different variations we could do on this. And of course, based on this, we've got another map tessellation, and like I say, we're not too sure what we're going on down in that corner, so that's where most of the points have gone now, because there's fewer points around to inform of what the function's doing, and that goes into our next example. And that basically, it looks a little bit worse here, but actually there's some interesting things with the uncertainty in this one which I'm not quite telling you. But iteratively, for doing this and trying to search and find these boundaries, as a matter of fact, I reckon we'd have points. There's some strange tessellations going in, so we'd have points here next time. We actually start to close in on what the true region looks like. So just to finish off, talk about the example. So clouds are notoriously difficult to model because of the non-stationarity in the processes. In particular, we're going to look at this coverage fraction from a particular model. So this is where we've got a genuinely expensive computer model. I'm told that it takes 3 hours per run with 240 cores on 760 teraflop Cray computer cluster, which is supposed to be really, really impressive, and I'm sure it is. But we're working on a cloud resolution model, which is working on a domain size of 40 kilometers by 1.5 kilometers. And we're running this model over a 12-hour modeling period as well. So if you're looking at about a time resolution of 2 seconds, and the grid mesh is relatively small in comparison to this, this is quite a expensive model, but with pretty small grid size as well. So expensive is the take-home message from that slide. So because it's expensive, we can only afford to run it 105 times. And Jill had come up with a design over a 6-dimensional parameter space. That's what we were looking at for this particular one. There may be other parameters that we might be able to free up in the future, but at the moment this is what they've got, and this is what we're looking at. And if we look at these 105 runs, this is a scatter plot. So here we've got cloud fraction on each one of these y-axes, and on the x-axis we've got these 6 different inputs. You'll see as we go across for many of these inputs, for some it's low, some parts it's low and some parts it's high. They're really kind of mixed up. So maybe on these 2 inputs there might be something a little bit different. So for low values of this input, it doesn't seem that there's this low behavior until we get to here where there's both low and high behavior, and maybe even clearer here where we've got low and high behavior here, then just high behavior. So if you remember what I said right at the start, the high behavior is a good behavior for this particular simulator, and we want to try and find the boundary between these 2 regions. So it's not going to be a straight problem we can see, because we can't just make the divisions upon these particular inputs, so there's something a bit more complicated. So when we try to emulate this and put our surrogate model around using these Voronoi tiles, we get a map model with 2 regions. One's got 87 centres and the other's got 18, which is very, very suspicious. So again, I reckon that we could probably describe this region in far fewer tessellations, but because we're just quite unstructured in the way that we're searching the tessellation space, where it's allowing it to get up. But of course, I could put more prior information into this and try and keep that lower if I like. The take home is that it boils down to the possibility of having 3 regions perhaps, or 2 or 1, but the most likely is that there's 2 regions, which agrees with what the experts were thinking. We were able to do 30 additional test runs, and these are the MSEs, the predictions. So the tree Gaussian process, the standard Gaussian process, just done very naively and not doing so well. And our naive Voronoi tessellation is doing better because we're able to capture that shape, essentially. That's all that's going on. So the question is, well, for the scientists, where is this boundary? So I went away and did my sampling technique, and I found loads of points that are on the boundary. And so I went back to Jill and said, look, Jill, here's your boundary. Done. Of course, this is pretty difficult to interpret exactly what's going on here. It's 6-dimensional space. It's difficult to visualize. So we thought about different ways of actually producing plots which might be more useful, but although I've not come up with anything which I'm really happy about yet. This is the next one. It might be a bit difficult to see because we were on kind of different shades of grayscale. Essentially, we've got the same kind of scatter plot there, but what's happening is for each one of the inputs we've got a grid box. So this is for a value of x5 and x6. We're saying for that particular grid box, if I look behind it into the other 4 dimensions, what proportion of points are in region 1, or the bad region, right? So that's the best that we can do at the moment, to have like a 2-dimensional projection of where this boundary is. I'm talking to other people about this particular problem. We've been thinking about trying to fit polynomials and things to the boundary points, because we can sample it very many times, so we might be able to do something a bit more interesting there, but we've not really explored that too much. So because we've got these validation points, we can rerun the analysis and try to get better at where the boundary is. So we also added an extra 30 points on top of the validation points that would help us to refine the region boundaries, and that's the difference. And if you can see any difference between that and what I showed before, though, you're very, very perceptive, because I'm not sure there is much difference there at all. But the good thing is that we've managed to find these corners of space where the model is doing something strange. So we can actually start to say, well, the model's operating well here, and why is it operating well here? Why is it not doing so well when we've got this particular combination of inputs, for instance? Is this really physical or not? Do we believe the model around this boundary? And all these kind of questions can start to be asked and answered, perhaps. So, given what we've done, then why should I stop at straight lines and convex tiles? When I first started out this work, I jumped straight into doing weighted, multiplicatively weighted Voronoi tessellations. I just thought, stuff the Voronoi stuff, that's all straight lines. I want to have curves in my space. What happens when you use this is essentially you get an extra parameter on each one of the centres, which makes it even worse. So it's terrible already for identifiability, but once you start adding in extra parameters like this, it's pretty bad. Although if we could constrain the space a little bit, then there's a chance that we can do something interesting. Of course, I use Euclidean distance to work out which tile we're on, but there's very many distances that we could have tried instead. So if I wanted something that was a bit more non-convex, but if I thought this kind of shape is what should be coming out, then I can use other distances as well. One thing that I didn't really say earlier on is I decided to use Gaussian processes on each one of the individual tiles because that's the regression tool that I'm used to using. Of course, we could have used any regression tool. The method, the Voronoi method, is just about giving us structure for dividing up our space so we can put different models on different parts of our space, right? So that is general. So we don't need to stick to Gaussian process at all. We can fit whatever we like to it. So just to finish off, I should say that these two references really did spark this work. So the work of Bobby Gramercy and Herbie Lee on the tree Gaussian process, and the Kim Malik and Holmes work looking at the 2D part of the Voronoi has led to this work, which hopefully will be coming out sometime this year. Thank you.
Any questions? Yeah.
So can you back to this red table where you compare the three different approaches? I mean, I've completely misunderstood what you did, okay? So forgive me if I said something. But to me, it seems here a comparison of a model that has no information about the discontinuity, a model that has some information about discontinuities being right angles, and there's something like the discontinuities are within polytopes, right? This element. Okay. Now, it seems to me what you are doing basically is a classification task and then a regression problem, right? Why do you don't take it from that perspective? I mean, this comparison for me is not very meaningful because it's the same like if you put the wrong prior, you get wrong results.
Yeah, but the numbers are half. This is half for those, so surely it's a good thing to show. You're absolutely right? So it's not fair. It's absolutely not fair what we've done.
Maybe not fair. It's like what you try to say with this, because essentially saying, yeah, if you put your wrong hypothesis, you get wrong results.
Right, so what I'm going for here is that many people are applying Gaussian processes to models and not thinking about what might be happening inside, right? So that's the only point, but you're absolutely right. And the other point that you make about why not treat this as a classification problem, well, you could have much richer divisions. If you could have a Gaussian process, if you like, over your classification space. And there's people pursuing this kind of idea as well. So this is just an alternative which maybe doesn't need as much information to tie those things down. So if you had information that these types of polygons were appropriate, then, but it's exactly what you're saying, it's having the right prior. Henry?
If you go back to the picture where you did the nice picture of Voronoi, can you go back to,
right back to that.
to the beautiful picture of Voronoi? Back. That's no, forward.
Well, that one do. Oh,
so, the dotted lines are the Delaunay tessellation, and they're all simplices. They're all triangles. So why don't you throw away the Voronoi and use those? The simplex is such a beautiful primitive. Your computation might be much easier if you use those as the primitives rather than the original Voronoi.
Yeah. So I could use any structure that I like, right? So if I wanted to use this kind of triangular thing,
Yeah,
which
you
is
can
a
use
dual,
any
which you
triangulation
get.
would be good. This is the most famous triangulation, really. It's the Delaunay triangulation.
So the dual, it is a dual, right?
It's the dual. This is the dual, yeah.
So you probably need more. You probably need more triangles, right, to get certain spaces. However, you need the same number of centers in order to define it.
Yeah, and also, it's the edges are defined between your original points. You don't have to redraw a complicated Voronoi.
Yeah, but I've enjoyed wasting weeks and weeks trying to find answers. Tony.
When you added the 30 points, you said before that you had many regions, many tiles making up your two regions. Did the number of tiles you needed reduce when you got 30 more points?
I'm not sure. Chris, did they reduce? He's not sure.
I'm not sure.
I'm a bit worried about how the MCMC is exploring the space. If I'm honest, I think it would just keep on going and adding extra tiles, even though they're adding nothing. Because what we're doing is we're sharing information across tiles. So if you add in an extra tile, it's not. Maybe it is doing something. There's a prior. Yeah, we have got a hard boundary on that. So yeah, it must come to a point where it just stops.
It's not so much about this work, but the fact that you have that triangulation in multiple dimensions somehow puts you ahead of another game that people are trying to play in generalizing those results. Let's say if you have the Gaussian covariance function, if it's a matern, then it's the unique solution to an SPD, and then you get the precision for free, and so you can do IMLA and all of that sparse cool stuff on huge data sets for nothing. And there's a lot of people trying to work out, can you do that for computer experiments? Like, you kind of have the bit that people are struggling with.
So we're learning that structure.
Yeah.
For free.
Yeah, like Serge was giving a talk on the idea of the triangulation, but everyone does it in 2D because they have spatial data. Santi was saying you might be able to get it in ND, but it's hard. You're doing it, and it took 10 years, so.
Yeah, so in different regions, let's say you have different length scale going on. So contrary to what the 3GP is doing, you're pulling in the information. Let's say in problems where there are very different length scales, will that help or?
No, so each one of the Gaussian processes we're doing it totally independently. So we have got different length scales and potentially different correlation functions operating on each one of the regions.
In your example, do you take different correlation pairs?
Yes.
Like Mattern for something and RBF for something?
In principle we could, but in our examples we don't.
No,
so it's
that's
all
what I'm
matern.
asking. So let's say you have a function which is sinusoidal at some region, and then you have a flat exponential function. So pulling in the information, will that help or deteriorate?
It would help. It definitely help. If you know more about, if you can build more into the correlation structure, then your predictions of things are going to be much better. But you can, because you're sharing information across the regions as well. That's.
But like if I have a smooth exponential function, and then I have a fastly varying trigonometric function, then I'm pulling that information.
Oh no.
So in your case, you're pulling both the information.
No. We're splitting it.
So you're.
No. So there's potential for us to fit totally. So at the moment, I'm saying yes, we're using matern across them all, but we're using matern with different length scales.
Yeah, no, I understood.
But we could have different correlation functions totally and learn those as well, and that would be far more powerful.
Yeah, that's what.
Running out of time, but.
Later.
All right. Okay.
Just a very quick one. If you put a separate GP in every cell, then you've got a lot of discontinuities all the way along all these boundaries. Is that
quite right?
Is that realistic? Can't you in some way constrain the thing to be continuous across boundaries by picking some constrained GP to or something like that?
Well, we're actually fitting Gaussian processes to regions which collections of tiles. So we're not having all the discontinuities, so it might have if we did put an individual. Although the original work, they did do that. where they had individual. But if we wanted to say constraints that we have matching at each one, it is possible, and there's ways that the covariance collapses to be quite nice on the boundary. But here we think that at the edge of the regions we've got real discontinuities.
Clayton, did you want to ask your question while we set up the
I
next?
just have a question just about in general. So, since you're in small dimensions, I'm just trying to figure out why do I need the Gaussian? What's the Gaussian process do for me? Why don't I just use a hierarchical basis, and then I can not only refine the boundary, but then I have everything. So, like, I'm just confused. I mean, like a piecewise constant approximation would do that.
A piecewise constant approximation would do very, very well in that example that I had.
But in high D, you can't do this at all. So in high D, the boundary is itself, in n dimensions, the boundary is an n-1 dimensional manifold. So itself is a high dimensional problem. So I'm just trying to, so in low D, I just use any hierarchical basis, local basis would do this, and it would give you an exact representation of the boundary.
Right. Yeah, that would be possible if we could propagate the uncertainty through that kind of thing. But the thing is that we want to be able to use this on very high dimensional problems. So the kind of even 60 is just the kind of taster for where we want to go. We want to be doing this in 20, 30 more dimensions, where we've got these really complicated computer models where they've got things. But in lower dimensions, then there's definitely things that we could do which would be
Voronoi
quicker.
algorithm, you can't scale it. I mean, even 3D is hard. Even 3D is extremely challenging for a Voronoi tessellation.
Well, it's challenging to know where the boundaries are, but it's not challenging to run the algorithm in however many dimensions I want.
I mean, it's just at the guess at the end. I mean, it's just k-means, right? At the end of the day.
It is. It is, and I hope that I can take some of the visualization techniques from k-means to make this a little bit better as well.
Okay, so final talk for the afternoon. Another Oak Ridge National Lab, cool talk, I'm sure, from Guangzhou